We're going to continue our work with scalar surface integrals now, and we're going to transition to vector surface integrals later in this lecture. So first of all, why don't we give a brief reminder on scalar surface integrals. So we work inside the 3D domain, and inside the domain we have a surface. Let's call this S. We have a function defined all around. It's a function of 3 variables. Again, technically, it just needs to be defined on the surface. And we would like to define the scalar surface integral of f along S. So in order to do that, we need a parameterization of the surface coming from 2 dimensions, let's say a domain D in the UV plane. And let's call this parameterization G of UV. This parameterization gives rise to a normal vector. I'm going to denote this by N of UV, and it will be the partial derivative of G with respect to U. By this, we mean that we take the partial derivatives of all the components of G. Actually, it might be a good idea to describe this in a more concrete way. So this function G of UV will look like this. So it will have 3 components. And when we say, for example, that we want to take G sub U, what we really mean is that we want to take the partial derivatives of all the different components. And then we do that with V. The 2 vectors that we get are tangent to the surface, and when you get their cross product, that becomes normal to the surface. And for the moment being, all we need in our formula is to integrate over the domain D. We pull back the function onto the domain of the parameterization simply by composing it with the parameterization, and then we multiply by the magnitude of the normal vector. Remember that that magnitude will really represent small or areas of small parallelograms that are generated by the tangent vectors. And that's our integral. And one thing that we said was that if we happen to integrate the function 1 along a given surface, then what we get is the surface area of S. And this can be thought of as both a definition and a computation, whatever you prefer. And before going on to vector surface integrals, we would like to do one more example, one striking example, and compute the surface area of the sphere. So let's try to discuss this in detail because it's a very, very interesting example. So you're looking at the sphere, and certainly there are different interesting options here. So let's say that it has radius r. And there are different options. So for example, if we wanted to parameterize it as a graph, certainly that wouldn't be possible because it's obviously not a graph. However, since we're looking for the area, we could just find the area of the upper hemisphere and double it. And the upper hemisphere can be considered as a graph. However, we're not going to go down that path. Instead, we're going to consider a much more interesting parameterization. The much more interesting parameterization that we're going to consider comes from the consideration of spherical coordinates and how spherical coordinates work. And that's why instead of denoting it by g of uv, in order to be a little more suggestive, let me denote it by g of theta phi. Now, here's how this works. Any point in the three-dimensional space has its Cartesian coordinates that can be expressed using the spherical coordinates. Now, if we take such a point and we actually fix the spherical coordinate rho to be equal to r, meaning the distance from the origin to be r, then we automatically restrict our attention on the sphere, and we're doing so by using two variables, and that actually turns out to be a parameterization. So the parameterization that we will have here on each component will have exactly the expressions of x, y, and z in terms of the spherical coordinates, and we will be missing just the and rho will be replaced by r. So we will have r sine phi cosine theta, r sine phi sine theta, and r cosine phi. And what is the domain of this parameterization? Well, it's pretty much the full range for each of the variables. So the domain is going to be for theta 0 to 2 pi. Again, here we have this little point that one can make of whether we should take open or open interval at 2 pi or closed. And we're being redundant by taking it closed because there are points that are going to be given twice, but the set of those points does not affect the surface area because it doesn't, its surface area is 0. It's a some arc. So times 0 pi, which is the full range for phi. And now the interesting part is that we will have to compute the normal vector and subsequently its magnitude. So this is a very, very interesting computation. Let's try to do this computation. So this will be g sub theta cross g sub phi. And now remember, r is constant here. We're taking the derivatives first with respect to theta. So this is going to be minus r sine phi sine theta, r sine phi cosine theta, and 0. Notice that the last coordinate does not depend on theta. And then when we differentiate with respect to phi, we'll get r cosine phi cosine theta, r cosine phi sine theta, and minus r sine phi. And this will be I, j, k. We have somewhat long expressions here, right? So we have minus r sine phi sine theta, r sine phi cosine theta, 0, r cosine phi cosine theta, r cosine phi sine theta, and minus r sine phi. And here, before we compute the determinant, there's this interesting property that we should consider, that if we have a rho from which we can factor out a certain quantity, then this quantity can go in front of the determinant. And theoretically, you can factor out anything you like, but here it's very convenient to see that you can actually, you have actually r and sine phi that are common. And of course, the third component is 0, and you can factor out anything from 0. And for the second one, you just have r. Okay, so I'm going to pull out all of these things so as to make my determinant look simpler. So I will have a rho square sine phi. What did you say? This reminds you of the Jacobian? Yes, it does, right? For spherical coordinates. Is that a coincidence? You bet it's not a coincidence. So in any case, let's not go over this any further here. Let's just finish this up. So we will have minus sine theta, cosine theta, and 0. And then we have cosine phi, cosine theta, cosine phi, sine theta, and minus sine phi. And okay, so that should be a doable computation. Rho square sine, r square sine phi. And then for the first coordinate, delete first row and first column. And what you're left with is minus cosine theta sine phi. For the second coordinate, delete first row, second column, and what you will get is sine theta sine phi, but you need an extra negative sign, so sine theta sine phi. And for the last coordinate, delete the first row and the third column, and what you will get is a little more complicated, right? So it's minus sine theta sine square of theta times cosine phi, and then you have minus cosine square of theta cosine phi. But I hope you all see the very simple simplification here, very simple simplification. Gotta love this, which is what? It's you factor out the negative cosine phi, and inside you have sine square of theta plus cosine square of theta, which gives you 1, and this is negative cosine phi. So let's see, altogether what we have rho square r square sine phi times negative cosine theta sine phi minus sine theta sine phi and negative cosine phi. And now we wish to find the magnitude of this. So what do we have here? We have a number, it's in particular a positive number. How do we know it's positive? Well, phi here is between 0 and pi, and sine phi in that range is positive. So all you need to do in order to compute the magnitude of this is just compute the magnitude of this vector and multiply it by r squared sine phi. So we will have that the magnitude of the normal vector, oops, not u and v, theta and phi, is going to be the number that we have in front, the positive number, no negative number that we have in front, times the magnitude of this vector, which is what? It's cosine square of theta sine square of phi plus sine square of theta sine square of phi plus cosine square of phi. So from these two, you can factor out sine square of phi. And of course, what remains behind is cosine square of theta plus sine square of theta, also known as 1. That's the Pythagorean theorem. And then finally, you will have sine square of phi plus cosine square of phi, which is 1. That means the whole monstrous root that you're looking at here is 1. So eventually, what do you get? R squared sine phi. So that's the magnitude of the normal vector. And since the function, the underlying function when we compute surface area is equal to 1, that's just the quantity that we have to integrate over what? over the domain of the parameterization. Okay, so what does that mean? That means that the integral that we have to find now is the integral over d of r squared sine phi dA, which will become the integral from 0 to 2 pi of r squared sine phi d theta, and this will be from 0 to pi d phi. This integral does split, so take away the constant, put it in front, then put the integral from 0 to 2 pi d theta, then put the integral from 0 to pi sine phi d phi, and let's see what we get here. So this will be 2 pi, obviously. This has antiderivative negative cosine phi from 0 to pi. I think we've seen this a few times. It's negative cosine pi minus cosine 0. It's negative 1 minus 1. It's 2. So the whole thing is 4 pi r squared. Okay, so that's the surface area of the sphere. And you know what? I mean, at first, there's nothing more to make of this. We can just take this answer and consider it as something interesting, something useful. But if we actually look at it a little more carefully, then we will realize that the volume of the ball was what? 4 pi r cubed over 3. The surface area of the boundary of the ball, which is the sphere, is 4 pi r squared. Do you notice anything interesting here? If you consider this as a function of r, then this is simply the derivative of it, right? I mean, coincidence? I don't know. Do coincidences happen twice, like as in go to the circle? What is the area of the circle, of the disk? Pi r squared. And what is the length of the boundary of the circle? It's 2 pi r. Oh, do you still have the derivative of pi r squared if you consider it as a function of r being 2 pi r? Yes, you do. That's certainly not a coincidence. And there are some very, very nice constructions where you can consider the surface area as being given through a construction involving the difference between the volumes of two balls and divided by an appropriate length that eventually shows you why you actually get the derivative. So none of this is a coincidence, of course, and we should just point out the interesting relation between these quantities. And with this very, very interesting computation, this is really a computation that goes beyond the graph parameterization that we pretty much discussed last time on when we introduced scalar surface integrals. With this, we can just go on to vector surface integrals. So again, it's a matter of analogies here. So I should write down what was the transition from scalar line integrals to vector line integrals. You may even be able to guess what the formula is going to be yourself. So when we have a scalar line integral, we had something like the integral of f of r of t times the velocity, times the speed, integrated over the interval of the parameterization, right? I mean, the picture is you have your domain that could be in 2 or 3 dimensions, you have the path C, and you have a parameterization r of t from an interval AB. Now, what was the vector line integral? So we had the vector line integral of f dr, and that was the pullback of the vector field onto the domain of the parameterization. dot, I mean, remember this is a vector, dot with the velocity vector from A to B. And again, the picture is pretty much the same. So you have C, but now this lives inside the domain that has a vector field, the vector field F, and then you also have the parameterization. What you have to remember here is that this has to be oriented, okay? And this is a very important remark to be made. So it's not, not everything is in full analogy. You need to have an orientation for your path. So let's see what the integral is for the scalar surface case. So we have a situation like this, and this ends up being the integral over the domain of the parameterization of the product of the pullback of the function with respect to that parameterization times the magnitude of the normal vector that can be attached to this specific parameterization. Again, it might be a good idea to draw a picture to know what we're talking about here. So here's your surface S living in 3 dimensions, and here is the parameterization by means of G of UV. So with this, can you guess now, can you pause the video and possibly guess what is going to be the vector surface integral? Here we're going to see 2 notations. So my favorite notation is this. So we have a vector field, and we're taking a vector surface integral, which is based on the normal direction onto the surface patch. But you also have this notation. So this is the notation that leads you closer to the analogy with scalar surface integrals. And the textbook that we're currently using for the underlying course has this notation. However, I'll be favoring the former notation. So can you guess, can you pause the video and guess what it's going to be? Okay, if you pause the video and took your guess, then here's the answer. So this is going to be the double integral of the pullback of the vector field by means of the parameterization integrated over the domain of the parameterization. And this is dot multiplied. So you take the dot product with the normal vector and you integrate over the domain of the parameterization. So that's what it is. But here, there's a very subtle point that needs to be made. So remember that in the case of the transition from a scalar line integral to a vector line integral, the new element that was added was the orientation of the path. And it only seems natural here that we will have something analogous. The question is, what do we mean by orienting a surface? And the answer is that the orientation of a surface is given by the choice of a normal vector. And it can be the normal vector at a given point where the silent assumption will be that you let it vary continuously through the surface. And the understanding will be that the normal vector that we get from that parameterization should point the same direction as the chosen normal vector for the orientation of the surface. If it doesn't, then what you simply do is you reverse, you take the opposite of that normal vector. So in other words, what one should say about this is that we have the vector surface integral that is initially defined needs to be defined with respect to a chosen orientation for the surface over which the integral is taken. So in the same way that a scalar line, a vector line integral had to be given with the orientation of the path, in exactly the same way, that needs to happen for a vector surface integral. So with all this, let's actually give some examples. So the first example goes as follows. So compute the vector surface integral of the vector field z minus x3 dot dn, where S is the triangle with vertices (1, 0, 0, 0, 1, 0, and 0, 0, 1), oriented with the upward normal. So here we should note that we will have to find ways of describing the normal, sometimes without drawing it. So here we have a triangle. Once we draw it, it will become rather obvious what the chosen normal is. And here's what it looks like. So we draw our coordinate system. So here are the 3 points that make up this triangle. And basically, we would like to orient it by using the vector that points upward. You could argue slightly upward. I mean, the angle is 45 degrees, so it's not really just slight. And one remark that we should make here, I mean, eventually you will find some normal vector. How do you know whether it's going to be the correct one or the wrong one? And the answer is that we will always have to find some sort of characteristic of that vector that tells us whether it is the right one or the wrong one. And in this case, this characteristic is going to be the third coordinate. So when you want something to be upward, then the third coordinate should better be positive. And that's precisely what we'll be looking for. So let's try to put the whole thing together. So first of all, let's note that the underlying vector field, that as you're going to see, such examples are quite labor intensive. So the underlying vector field is z minus x, comma 3. And the parameterization here is going to be simply a graph parameterization because this is the plane x plus y plus z is equal to 1. That's the equation of the intercepts. And it can certainly be considered as a graph if you solve for z. And the parameterization that we're going to consider will simply be the graph parameterization. So g of uv will be u comma v comma 1 minus u minus v. And the domain of the parameterization is what? It's the domain of the function whose graph is what we're looking at, which is simply the projection of the triangle onto the xy plane. So D is simply, let me draw it and then describe it. So here's your UV plane, if you like, which is taken to be exactly the xy plane that we have in the picture. So this is 1, which means that this is the line u plus v is equal to 1, or you might argue it's v is equal to 1 minus u. And the description that I'm going to choose so that I'm ready to go into the integral is that v is between 0 and 1 minus u, and u is between 0 and 1. So that's the domain of the parameterization, right? And now let's find the normal vector. So the normal vector is going to be g sub u cross g sub v. And this is going to be 1, 0, negative 1 cross 0, 1, comma, negative 1, which is I, j, k, 1, 0, negative 1, 0, 1, negative 1. And again, you get a constant vector. That's a very favorable situation. And here you will get 1. The middle coordinate will also be 1 because normally you get negative 1, but you need to remember that since we're dealing with determinants, that we multiply by an extra negative 1 here, so 1 and 1. And what really matters here is the last coordinate. Last coordinate is positive, and that really adheres to the orientation that was chosen in the beginning. So that means that it's the correct normal vector that we're considering here. Had it been negative, we would have simply multiplied the vector by negative 1. And of course, one might argue, what, you just out of the blue multiply by negative 1? Well, all you need to think in order to understand why this is fully justified is the fact that what this really amounts to is listing the variables in the opposite order. So if instead of looking at the function of uv, you look at the function of vu, which of course for the sake of the parameterization, nothing changes, then immediately you're going to get the opposite normal vector. That's one way to look at it if you want to consistently take gu cross gv. But you might argue that why not take gv cross gu? I mean, there is, again, no particular reason why you shouldn't do that. Okay, so let's compute the integral. So let's pull back the function to the domain of the parameterization. What does this mean? This means that we have to compute f of u v 1 minus u minus v. Where did I find this? Remember, that's my parameterization, which means that everywhere I see a u, everywhere I see an x, I should put u. Everywhere I see a y, I should put v. Everywhere I see a z, I should put 1 minus u minus v. And so this will be 1 minus u minus v and minus u and 3, right? And what do I do next? Next, we take the dot product of the pullback by the normal vector. So this is 1 minus u minus v minus u, comma 3 dot 1, 1, 1. A very nice, convenient situation. So what do we get here? We get 1 minus u minus v minus u plus 3, which is going to be 4 minus 2u minus v. And that's what we need to integrate. We need to integrate it over what? Over the domain of the parameterization. So eventually our integral will be the integral over d of this integrand 4 minus 2u minus v dA, which is an iterated integral. You cannot split this because the endpoints are not constant. So you're going to go from 0 to 1 minus u dv, and then from 0 to 1 du, and you have 4 minus 2u minus v. Let's do our integration. First integration will give us 4v minus 2uv minus v squared over 2, and you want to go from 0 to 1 minus u. The whole thing will be from 0 to 1 du. And this will be 4 times 1 minus u minus 2u 1 minus u minus 1 minus u squared over 2 from 0 to 1 du. And well, I could leave it as that, and I'm afraid I'm going to make a numerical error if I continue with this, but we need to continue. So this will be what? It will be 4 minus 4u minus 2u plus 2u squared, and then you will have minus 1/2 plus u minus u squared over 2. Okay, I think we're good here. We have to take this from 0 to 1 du. Common wisdom here would be to just make this as concise as possible. But you know what? All these integrations are so simple. So if you want to integrate 4 from 0 to 1, you will obviously find 4. If you want to integrate for u, the antiderivative of u is u squared over 2, so you will find minus 2. And then for minus 2, you will find 1, so minus 1. For 2u squared, you will find plus 2/3. For minus 1/2, it will be minus 1/2. For u, it will be plus 1/2. And for minus u squared will be minus 1 over 6, right? So can we add these things together? So we'll have minus 1/2 plus 1/2. Then 4 minus 2 minus 1 is 1. And then we have 2/3 minus, so this whole thing is 1. And then we have 2/3 minus 1/6. That's 4/6 minus 1/6. That's 3/6. 3/6 is equal to 1/2. 1 plus 1/2 is 3/2. If I had to bet, I would say I've made some mistake, but in any case, I just wanted to demonstrate how to complete the exercise. The last thing you should worry about is the final computation. Everything that comes before it is what is important. But I think it's a good thing to bring the computation to an end, even at the risk of having done some small mistake here. In any case, that's our first example of a vector surface integral. And I guess it would be a good idea to do one more example so as to demonstrate a completely different situation and actually a completely different parameterization. And here's what this is. So let's do the following example. So one thing that I haven't mentioned yet is that everything that we're looking at here, the vector surface integrals that we're computing today are flux integrals. So they measure the flow of your vector field through the surface in the direction of the normal, the direction that has been chosen. So, okay, so what do we have here? So as an example, as a second example, let's take compute the flux, now I should say, of x1 negative 3 dot dn, where, now let's make this interesting, where S is the part of the cylinder x squared plus y squared is equal to 1 in the first octant for z between 0 and 3, oriented with the outward normal. There's a lot to unpack in this. Description, and let's try to sketch this domain, because the last thing you should worry about here is the function itself. It's really the domain that is the most important component, meaning the surface. So what you have here is this part of the cylinder, right? You have radius 1, and it's going all the way up to height 3. And it's oriented by using the outward normal. And what really matters is to try to identify it at one point. So let me change my color here and draw a normal vector that points outward at this point. And what is this point? This point is the point 1, 0, 0. Okay, so I drew this normal vector. And pretty much what you would have to do is take this vector and travel it, carry it around on the surface in a consistent way without flipping it in order to get the normal at every point. Okay, and what is the vector? The vector is certainly one that points toward the positive x-axis, so it will have a positive first component, and the other two components, since it lies on the x-axis, will be 0 and 0. I'm saying this because in the same way that we identified the correct vector, that normal vector that we obtained from the parameterization before, in exactly the same way, we will have to do it now. However, what we will be looking at now is the first coordinate, because the first coordinate has to be positive. And let's see how this comes out. Now, we want a parameterization of this cylinder. How do we do this? Well, the first example that we did today on scalar surface integrals, in particular on the surface area of the sphere, took advantage of spherical coordinates in order to introduce a certain parameterization. We're going to play the exact same game with cylindrical coordinates here. So what is constant is the radius on this surface. So pretty much I'm going to change the other two to vary the other two cylindrical coordinates, which are the angle theta and z, in order to obtain everything else. And for that reason, again, allow me to write the parameterization in terms of theta and z to suggest that it comes from the cylindrical coordinates. Here, somebody will certainly see an inconsistency in me using z, which is one of the Cartesian coordinates. So yes, I'm being a little inconsistent here. However, what will be the parameterization? So I have to list simply the cylindrical coordinates. And what are the cylindrical coordinates? Or rather, what are the coordinates of this point with respect to cylindrical coordinates? And the answer is x, y, z, expressed using r, theta, and z. So it's r cosine theta, but r is 1 in this case. You know what? Maybe I should make it 4 so that we can see all what is going on. So this will be 2, and this will be 2, 0, 0. Okay, so let's make it. I'm sorry I changed the radius in the middle of the problem, but I think it's useful to see what it's going to look like, because if it was 1, then you wouldn't see anything. Now that the radius is 2, I'm going to put 2 cosine theta, 2 sine theta, and z. So what I really did is I took my random point in the 3D space. I considered its expression of its Cartesian coordinates using the cylindrical coordinates, r, theta, and z, and I fixed r. The moment you fix r, you find yourself right on that cylinder. Well, you need to further specify theta and z so that you get the exact piece, the exact surface that is here, but that's quite simple. So my domain is going to be simply from 0 to pi over 2, because I'm in the first octant, and that translates first quadrant for theta, and 0 through 3 for z. Okay, and that's my parameterization. So the underlying vector field here is f of x, y, z is equal to x, comma 1, comma negative 3. And the normal vector with respect to theta, comma z is going to be g sub theta cross g sub z. And this is going to be, we're going to have minus 2 sine theta, 2 cosine theta, and 0 cross with 0, 0, and 1. Let's see what we get here. I, j, k, minus 2 sine theta, 2 cosine theta, 0, 0, 0, 1. So this is going to be a delete first row, delete first column, you will get 2 cosine theta. Then delete first row, delete second column, you will get negative 2 sine theta. It's the middle coordinate, so that will give you 2 sine theta. And finally, delete first row, third column, and that will give you a 0. And that's your vector. So now the question comes up, is it the correct one? Okay, so how do we know whether it's the correct one or not? This point, the point 2, 0, 0, in terms of theta and z, what is it equal to? So theta at this point is 0, because it's the angle with a positive x-axis of the radial segment connecting the point to the origin, and z is equal to 0. Okay, but if you set theta is equal to 0 here, what do you get? So I'm specifying the specializing the normal vector that I got for the specific point to see if it gives me the right vector. If it gives me the right vector for that specific point, because of the continuity of the choice of normal vectors, it's going to be the correct normal vector everywhere. And of course, if theta is 0, what I get here is 2, which is positive. It certainly points the right direction that I had in the very beginning, and that's the correct normal vector. So this is the correct normal vector. Okay, so what do we need to do next? Pull back the function, the vector field onto the domain of the parameterization. Well, here it's kind of funny. So you will have to do 2 cosine theta, 2 sine theta, z, which means what? Wherever you see x, you put 2 cosine theta. Wherever you see y, you put 2 sine theta. Wherever you see z, you just leave it as z. Okay, that's sometimes the confusion that can be caused, but I think it's very minor in this case. So I have an x that will become 2 cosine theta. The other two components are constant, so I don't have to worry about them. And when I take the dot product of the pullback dot with the normal vector, that will give me 2 cosine theta, 1 negative 3, dot 2 cosine theta, 2 sine theta, and 0. And this is equal to 4 cosine square of theta plus 2 sine theta. So this is what we need to integrate. And we need to integrate where? Over this domain. So this is going to be the integral from 0 to pi over 2 d theta, integral from 0 to 3 dz of what? Of 4 cosine square of theta plus 2 sine theta. Sometimes I've had students ask at this point, okay, so where's the Jacobian? There's no Jacobian. We're not doing a change of variable. I know that the whole process really reminds us of what was going on back there. The truth is that you can take this integral and make it look exactly like an integral that you have in the context of change of variable. But the whole process is not equivalent step by step. So here there is no Jacobian. If you like, the Jacobian was already contained in the consideration of the normal vector. But let's do this computation. This integral does split, so we will have 0 to 3 dz times the integral from 0 to pi over 2 of 4 cosine square of theta plus 2 sine theta d theta. The obvious challenge here is the 4 cosine square of theta. Well, not such a big challenge. Remember your double angle formula. Cosine of 2 theta is equal to cosine square of theta minus sine square of theta, which is the same thing as 2 cosine square of theta minus 1, meaning that cosine square of theta is cosine of 2 theta plus 1 over 2. And this will mean that 4 cosine square of theta will be simply, so this will be simply integral from 0 to pi over 2 of 2 cosine of 2 theta plus 2 sine theta d theta. The antiderivative should be pretty straightforward here, so it's going to be sine of 2 theta plus 2 theta minus cosine theta from 0 to pi over 2. When you plug in either 0 or pi over 2 in sine of 2 theta, you get something which is 0, which because you get sine of 0 or sine of pi. For 2 theta, you get pi. And finally, for cosine of theta, you get cosine of pi over 2 is 0, cosine of 0 is 1, so you would get minus 1. Okay, so you need to multiply this by this integral, which is 3, so the whole thing is going to end up being 3 pi minus 3, which is our final answer. A very, very interesting computation. And what makes it interesting, what makes the whole problem interesting is the unusual parameterization. So to recap, in terms of parameterizations that could have been used both in the context of scalar surface integrals and vector surface integrals, we've seen the graph parameterization, we've seen the parameterization that is based on spherical coordinates, and we've seen the parameterization which is based on cylindrical coordinates. And that's pretty much everything that we're going to have. We're not going to see any further parameterizations, which of course can occur. One of the things, of course, I should add here is that when we're looking at graph parameterizations, they do not have to be in terms of functions that are expressed as functions of x and y. They could be functions of y and z or functions of x and z. So we should just leave that possibility open. Personally, one little game that I like to play in those cases is if somebody hands me an integral that where I don't particularly like the fact that I have to work with a function of x and z, let's say, I could change z to y and y to z and eventually work with an integral involving a parameterization of a graph parameterization in terms of x and y. So you can change the letter variables any way you like, as long as you are consistent with the domain and their occurrence in the integrand. But you know, there's no problem to do it with modified parameterization in terms of not just x, y, but other variables too. Very, very interesting things. And the only way to become comfortable with this kind of theory is to actually do this example several times, try to, freeze the recording, do your own work, make sure that it corresponds to what was written, or that at least it's consistent. Okay, thanks for watching.